Hi there, and welcome to the 9th lecture on the quantum field theory course. So in the previous lecture, we started to introduce the idea of trying to describe scattering processes, which we get in interacting theories. And we introduced two ideas, which at the minute sit separately. So this idea about an S matrix describing what I call in and out states, or sometimes called asymptotic states. And then we introduced this separate picture for quantum mechanics, but also for quantum field theory, called this interaction picture, or Dirac picture. So I want to begin this lecture by tying together those two ideas. So tie together the idea of the S matrix together with this interaction picture, and in particular with this time evolution operator that we saw at the end of the last lecture, which tells us how states in the interaction picture evolve with time. Okay, so we're going to start, as I said, tying together those two ideas. So tying together the S matrix, which is an object, we said, which is important and interesting, and time evolution operator. This was this operator we wrote down at the end, which was, we can write it as T1. Well, let's do T2, T1. It tells us how to go from one interacting state to another. Okay, so let me state the result that we want to use, or rather we want to show, and then we'll spend some time arguing for why it's true. So we want to show that the S matrix can be expressed as the limit as some time goes to infinity, e goes to infinity, of this interaction time evolution matrix. Okay, so in other words, the S matrix is going to be the form of this time ordering operator times the form that we find for this matrix U. So it's the exponential e to the minus I, we're setting the limits minus infinity to infinity, of my interaction Hamiltonian depends on time, so I'll label it by some dummy index t prime. Okay, and the important point is that we need this time evolution operator for this expression, or for the expression for U to hold. Okay, so what we want to show is this first bit, that we can identify S with this time evolution operator. Okay, so to do this, let's go back and think about our picture of scattering. Okay, so let me draw this. So we think about scattering happening over some time, where we approximate it as going from minus infinity to infinity. So, I mean, in a real experiment, the reason why this is a good approximation is because the time scale where particles interact is typically actually very, very small. Right? So think about a typical time scale for a strong interaction process. It's around 10 to the minus 24 seconds or something, 10 to the minus 20 seconds, very, very short. Even weak interaction processes, which are weak, happen over time scales of 10 to the minus 10 seconds. So, you don't have so the infinities we're talking about here are relative to those 10 to the minus 10 seconds. So very quickly you end up in, after a second or half a second, it's as effectively as if you're at time plus and minus infinity. Okay, so what's important about scattering theory, if you remember, is that we should really divide our process into three regions. Lines. So we've got this region in the middle, which is going to be our interaction region. This is where all the complicated parts of the scattering process happen. Here we imagine that our interaction Hamiltonian is actually switched on. And then we have these states at plus and minus asymptotic infinity, where we approximate the effective interaction as being zero. So in other words, at infinity, the states, our particles, behave as if they're free particles. So this is true for, like a potential that goes like 1 over r to the 2.5. Okay, so you've got some potential that drops off with distance. So as you move away from the interaction zone, the potential gets weaker and weaker, or the force between the particles becomes weaker and weaker. So you can make this a little bit more formal in scattering theory and sort of classify the types of potentials that are allowed for this picture to hold, so that HN really is approximately 0 at plus or minus infinity. We're not going to go into those details in this short course, okay? But you can certainly read about it in different scattering books. So what happens? The main thing with scattering theory, as I said, is we deal with these in or out states or asymptotic states. So asymptotic states are defined at times plus or minus infinity. Okay, so let's imagine a specific scattering process. Let's imagine we have particles labeled by their momenta. So we have some particle momentum Ka, momentum Kb, and it's going to end up in some state with P1 and with P2. Okay, so we want to understand the scattering process where these initial particles end up with in potentially some different state. Okay, so obviously in the real process, what happens is that these particles will come together some way around some reference time, let's call it t equals 0, and then they'll leave again. Okay, so in the full theory, this process with these black dashed lines is what happens. But the difficulty is that for the quantum field theories that we know about, we don't know how to model the theory in this central bit. So we don't know how to solve the theory exactly with all of the interactions switched on. So the only bits that we know how to describe are the bits out at asymptotic infinity, where it's just the free theory that we've looked at in a lot of detail. So the idea then is to try and express everything in terms of these states out at plus and minus infinity, which are these actually free states, or these in or out states, or these asymptotic states. Okay, so out here we have word asymptotic states. As we said, these are special states because they involve that essentially an interaction term which is 0. We have that with our initial states, and we have the same thing with our final states as well. Both are asymptotic states. As I said, the advantage so these are good states. They're good because we know how to describe the free theory. We know how to quantize it. We know lots and lots about the free theory. Okay, so in practice, that we want to somehow relate our theory to experimental measurements in some way, so we can get a direct comparison between the two. And as particle physicists, I'm sure most of you know that the way we do that are through cross sections. So in the end, we really want to calculate. We want to calculate a cross section, or a differential cross section, or something related to a cross section. So we can do this comparison between theoretical and experimental quantities. Okay, so we want to calculate this cross section. Now in this short course, I'm not going to go through the full details of how you can calculate the cross section, just because we don't have time. But let's pull out the most important part of what a cross section depends on. So the most important thing that a cross section is going to depend on is the amplitude for the scattering process to occur. And I hope this intuitively makes some sense to you, right? So we're dealing with some initial quantum states. We have some amplitude for the initial state, and we're going to have some amplitude for the final state. And if we're asking, how probable is it that Ka is going to end up in the states P1 to P2, well, from quantum mechanics, we know that's going to be the amplitude of these states squared. Okay? And a cross-section obviously is asking a similar question. It's asking, how likely is it that this scattering process happens where I go from this initial state into my final state? So I hope you can trust that cross sections really do depend on amplitudes squared. I mean, obviously there's other factors as well related to the phase space for the final states. So that's the bit we're not going to touch. We're not going to go into those details. We're going to just work at the level of the amplitude. In terms of the process that we have above, where we have this 2 to 2 process, you write the amplitude as A. The 2 to 2 scattering process above is going to be the amplitude that my states Ka, Kb, these initial states, end up in my final states, which I'm labeling by P1 and P2. And this is, the scattering amplitude depends on the overlap with the true states in the theory. Okay, so in an ideal world, you would just take the true states and just do this, work out what the bracket with the true states is, and that would tell you the amplitude. And I've put the little subscript h here just to tell you that we're working in the Heisenberg picture here. But as I said, in practice, we can't solve for the full true theory exactly. Instead, we use this idea of the S matrix. The idea of the S matrix is that this amplitude be written in the following way. So again, it's the overlap of states. Now we have this special operator, the S matrix. What it does is it relates the asymptotic states. Asymptotic. I could just write ASY. So this is the asymptotic states. Again, we can do it in the Heisenberg picture. Okay. So we're making this simplification. Here, we're only working with these asymptotic states that we know how to deal with. But we're now saying, okay, we're working with states we have to deal with, or we know how to deal with, but we have to introduce this operator S that takes us from the asymptotic initial state to the final state where we do the overlap. Okay, so how do we relate this to things that we actually know how to calculate, or how do we relate it rather to the to this time evolution operator, which I said is what we want to do? Well, let me tell you the argument. So just to remind you, so we're dealing with Heisenberg states here. The time evolution operator is related to the states in the interaction picture. So we want to go from this Heisenberg picture to our interaction picture. So let's go ahead and do that. So to remind you, in the previous lecture, we showed that the interacting state can be written in terms of the Schrödinger state. I'll write with an S, with this factor e to the I h naught t. So h naught is the free part of the Hamiltonian. So we break our Hamiltonian into two pieces, h naught and h int. And this is good, but it's not what we want. Okay, we want Heisenberg states, so we have to relate our Schrödinger states to our Heisenberg states. But we know how to do that. Time evolution of the Schrödinger states is simply e to the minus I h t, where now h is the full Hamiltonian. And then we're saying that the Heisenberg state, the h, is defined to be the state at our reference time 0. This is what we did previously when we introduced the Heisenberg state. So we said the Heisenberg state doesn't evolve with time. It's the value of the Schrödinger state at a reference time, which we're going to choose to be t equal 0. Okay, so what you can see is that the interaction picture and the Heisenberg picture match up at a very special time at our reference time. But t equal to 0, we see that our interacting state is simply equal to the Heisenberg state, okay, because we set t equal to 0 and these exponential factors, and we just get the unity operator. Okay, so at a certain reference time, these states align. Okay, so that's good, because this allows us to write the expression above in terms of not Heisenberg states, but in terms of interacting states. Okay. So you notice here I've been considering the interaction with the full theory, right? This is the full Hamiltonian that's entering here. Okay, so we can actually put on the subscript true here. So it doesn't just hold for asymptotic states, because it involves the full Hamiltonian, involves everything, the full theory. At t equals 0, our interacting state is the same as our Hamiltonian state. This allows us to rewrite the top line. We can write 2 to 2 element, which is what was it, P1, P2. True state is exactly the same as the states P1, P2 at t equal to 0 with Ka, Kb at t equal to 0 in the interacting picture. Okay, so that's just a straightforward rewriting so far. The next thing we want to do is to relate it to our expression with the S matrix. We want to relate it to our asymptotic states, which are defined at times of plus and minus infinity. In other words, we have to evolve our states from t equal to 0 to t equal plus and minus infinity. Again, we know how to do that. The general result is that the interaction states are simply governed by this time evolution operator. So to go from an interacting state at t0 to a state at times t, we use this time evolution operator. So we can use that then in our expression for the amplitude, 2 to 2. So we're going to evolve our states. So let's do the k states first. This is going to be u. We want to go 0 to time minus infinity. Then we're going to have the states Ka, Kb at time equal to minus infinity. We're still in the interaction picture. And then we want to evolve our other states, P1, P2 to t equal to plus infinity. Here we'll use the matrix infinity 0. Interactions. Okay, so now we use a nice property of the interaction picture, which is, mind you, so in the interaction picture, time evolution is determined or governed by the interaction Hamiltonian. Okay, now let's think about what happens at time equal to plus or minus infinity. So to remind you, at times plus or minus infinity, we're assuming that this interaction becomes so weak that it's effectively 0. Okay? In other words, these become so at time plus or minus infinity, we have that the interaction is approximately 0. Implies that our states at plus and minus infinity are simply our Heisenberg states, or asymptotic Heisenberg states, okay? Because the interaction bit is 0, so they're acting freely and they aren't evolving with time close to infinity because the interaction bit is set equal to 0. Okay, so we can then use that fact in our amplitude to rewrite this as the state P1, P2 in the Heisenberg picture, and what's asymptotic state with our time evolution operators. A, Kb, which is precisely the form of the definition with the S matrix in it. So we have asymptotic states on both sides, and we have an operator sandwiched in between. So we must be able to identify this object as the S matrix. So this gives us a link. Let me put a hat on it because it's an operator. All of these things are really operators. This gives us a link between these time evolution operators. So there's a property of the time evolution operator that we won't prove. I'm just going to state it. But it makes some intuitive sense where if we evolve from a state minus infinity to a 0 and then evolve it from 0 to infinity, this is the same as simply evolving it in one step. So from minus infinity to infinity. And to remind you, this is precisely what we started out that we wanted to show. So we've shown that this S matrix then be written in terms of this time evolution operator from minus infinity to infinity. And in the previous lecture, we showed, or we found, there was an expression for this matrix in terms of an exponential. So this is our final expression. The nice thing we have, we've been able to relate our S matrix to the interaction Hamiltonian. So it enters in this peculiar way where we have an exponentiated interacting Hamiltonian with this time evolution operator so that we get the correct expression. Okay, so we have now an expression for this S matrix. So the S matrix is the most interesting part of the theory. So it's something that we would like to be able to calculate in order to work out scattering amplitudes and therefore relate them to cross sections later on. It turns out that this is not entirely trivial. So let me describe a method due to Dyson's expansion method, for how to actually go about calculating this S matrix. So, as I've said, in practice, for interacting theories that we know about, this matrix, this S matrix, cannot be solved exactly. We have to come up with some other scheme to actually make progress. The approach we take, rather than solving it exactly, is we're going to series expand the exponential. And do a perturbative expansion, which is obviously going to be true if that e to the minus whatever the exponent is a small parameter. Okay, so this is what we mean by Dyson's expansion. We're expanding the exponential. Okay, so in practice, what does this mean? We're going to write S as this time evolution operator. So we've got the identity operator, minus I, minus infinity to infinity, prime, hi, t prime, so on. You'll have the minus I squared terms and so on. But let's just manipulate this a little bit, or rather we're going to manipulate each dt term that appears in every part of the expansion, apart from the identity piece. So we're going to recall one fact. Okay, so we know that we can write our Hamiltonian in terms of a Hamiltonian density. Okay, and I guess I should explicitly put in the time dependence. So these are time dependent operators. So we can rewrite our Hamiltonian in terms of this curly h. Okay, what does this mean whenever we do an integral over time then? If we consider dt hit, which is what we're going to have in every term in our exponential, well, we're going to have a dt times d3x, or we're going to write this as d4x. So we're integrating over all space-time coordinates with this Hamiltonian density. So it's going to be the Hamiltonian density which we're actually going to use in our expansion. So just as a reminder, in this phi to the 4 theory that we've been looking at, we worked out what the expression is for h int. Okay, so h int, our theory, not in the interaction picture. Okay, so this Hamiltonian density is in the interaction picture. But we know how to move between our different versions of mechanics. Okay, so our hi, our time dependent operator, is simply going to be defined by hitting with the front with an e to the positive I h naught t defined with an e to the minus I h naught t. So this is a relation that we worked out between operators in the previous lecture. So for this example above, from phi to the 4 theory, we've got our lambda over 4 factorial factor, which I'm going to pull out the front. And then we need to sandwich this phi to the 4 in between an e to the plus I h naught t and an e to the minus I h naught t. Okay, so we need to put in 4 phi factors, fields. I'm writing it in this way because what we want to do is to insert the identity in between each of these terms. Okay, and I'm going to write the identity in a special way. Write it as e to the minus I h naught t, e to the plus I h naught t. And if we do that everywhere, okay, we see we get this pattern where we have e to the I h naught t, phi, e to the minus I h naught t, and that will appear 4 times. Okay, we put in all of the terms, and that means that allows us to write our interacting Hamiltonian density as top and bottom. We can write it in terms of a field now in the interaction picture. We're going to have 4 of these fields. Here, this interaction field. So our fields are operators, just as we said that the Hamiltonian density in the there it is. Hamiltonian density in the interaction picture has these time evolution bits in front of it with the free part of the Hamiltonian. So too, we can define our interacting fields in that picture. Now, the advantage again of these interacting fields, as you can see, is that the time evolution is just governed by the free part of the Hamiltonian. Okay, and the advantage of the free part of the Hamiltonian, this is the part of the theory that we know how to deal with. Okay, so we know then we can just use all of the results that we already have for that we worked on in the first 5 or 6 lectures, which is what the time-dependent interacting theory is going to look like. It's precisely the form that we derived previously. So you do it explicitly. So in terms of the 4 space-time components of x, y, z, and t, our field can simply be expressed as before. Have all of the same factors, the d3p, that it is 1 over square root 2 omega p. And these operators with the free Hamiltonian will tell us about the time dependence of our creation and annihilation operators. What they'll tell us is, well, we'll end up with precisely the result that we found in the free theory, which is that all of the time evolution end up in the e to the minus ip dot x. Okay, so we end up with precisely the expression we had before. Okay, so just to summarize, so we're going to calculate our S matrix with an expansion. Okay, and our expansion is going to involve, I'm not going to write the full Hamiltonian, we're going to use the Hamiltonian density integrated over d4x. And we need to express our Hamiltonian density in this interaction picture in terms of fields in the interaction picture. So we do that in a straightforward way in this case. And the advantage of the interaction picture, the field operator, evolves in exactly the way that we worked out for our free theory. So we know what the expression for this interacting field is. Okay, so we've discussed how to relate S through this time evolution operator. And we've said that we're going to calculate S as an expansion, this Dyson's expansion. So in general, there's a sort of 5-step process that you can just go through every time you want to calculate a scattering amplitude. So that's what I'm going to go through next. So it's a very standard procedure. If you follow these 5 steps, turn the cranks, you should be able to get to your answer, to the scattering amplitude. Let's do it in the context of an example. So the example that we've already been considering, where we have 2 particles labeled by their momenta, A and B, Ka, Kb, scattering into the states P1, P2. And let's do it in this phi to the 4 theory. That obviously includes interactions. Okay, so as I said, 5 steps to follow. So that's what the first. So the first is, not describe. We want to decide on the process. So we've already done the first step. The process we're interested in is this 2 to 2 scattering process above. We want to decide on that. And then once we know that, we want to write the amplitude in terms of vacuum states. Remember, vacuum states we labeled with 0. Okay, let's see what that means in practice for this example case. So we're considering this 2 to 2 scattering amplitude. And we said that with the use of the S matrix, this involves some asymptotic states or S matrix sandwiched in between them. Okay, so we want to write this process, this amplitude, in terms of vacuum states. So that's also something we know how to do, because these asymptotic states, we know how to deal with them. Okay, so we know the advantage of the asymptotic states, remember, is that we use the formalism from the free field theory. Okay, so we know how to write momentum states in the free theory. So it's going to be this factor root 2e for each state. So we've got root 2 Ka, root 2 Kb, and then we need to have a correlation operator for the Ka state and a correlation operator for the Kb state acting on the vacuum. Okay, so this is just the definition of a momentum state we used in the free theory. And okay, I'll not write down the full expression, but obviously there's a similar expression for P1, P2. The asymptotic state with P1, P2 in it. Okay, so that means we can rewrite the amplitude above. Do the 2 process then. Okay, so we have all of these square root factors. Fine. And then we get to the interesting bits. Okay, so let's rewrite it in terms of the vacuum. So we've got 0, and we're going to have a P1, a P2. So obviously we have to take the conjugate. When we take the conjugate of the creation operator, we get the annihilation operators. That's why it's annihilation operators with P. And then we have S as before. And then we're going to have A, B. Okay, so we have succeeded in our first step. Okay, so we want to do that for any process, and we're doing it for this particular 2 to 2 process. Since the bit we're going to be most interested in isn't going to be this square root factors, so just to save myself from writing this endlessly, which has no real content in it, I'm going to focus on the bit which is interesting, that we want to think about more, which is the bit between the vacuum states. So I'm going to call this little bit is between the vacuum states A tilde 2 to 2. And so this then is the bit that we're going to focus on going forward. Okay, so that's step 1. Okay, so next, let's think about step 2. So that was the end of step 1. Okay, so step 2, we have this S buried in this amplitude still, and we want to deal with that. So as I said before, we're going to deal with S by expanding it using this Dyson expansion. So that's going to be straightforward. Okay, so we've already written down what this expansion is. So just to remind you, 1 minus I. Now we're using this d4x, and we're using the Hamiltonian density, base time point x. And then we'll get other terms as well from the exponential. So we get, let's write down second term as well. So we can do d4x, d4y, hix, hiy, and it goes on and on and on. Okay, so you just keep going. So that's the sort of general expression. Let's think about phi to the 4 theory. Okay, so we know that hi is lambda 4 factorial phi, put in the label x over here. Okay, so we know that this is true. So I'm going to drop, so in principle, I could keep writing i's here, but again, just to save me writing this all the time, I'm going to drop the I, but you should understand that this is the field for operators. This is the field in the interaction picture, but as we said previously, the advantage of being in the interaction picture is we know how to expand this. We expanded it before, and it's just the same expansion that we had in the free theory. Okay. So what does this mean in practice? Well, for this phi to the 4 theory, we're going to simply have 1 minus I lambda over 4 factorial for x, phi for x. We get the squared term. So we'll have lambda over 4 factorial squared for x, for y. Okay, and oops, plus so on. Okay, so you can in principle just keep going with the expansion, but we're going to stop at that point. Okay, so that's step 2. We do this expansion of S using the Dyson expansion. Okay, so step 3 is going to be straightforward. So we take what we have from step 1, which is the amplitude in terms of vacuum states, but we still had this S. Now we need to simply plug in our expansion for S. So why don't I copy this down so that I have it on the page below. Quick way. So just so it's on the screen. So we're calling this A tilde. Okay, so we're just going to substitute in the expansion for S at the top of the screen into this expression. So relatively straightforward. I guess one thing maybe to be careful with, we're going to have this T operator, which time orders everything. So remember, this moves later things to the left. Okay, so it'll put all of my things which happen later on over to this side of the expression. So I can pull, in principle, I could write T in here with a lot of terms, but you can also see that I can just pull it out to the front because the stuff here already is, this does happen later on. This is what happens at the very end of my expression. Okay, so I'm going to pull the T all the way out to the front. But it's going to sit outside a large square bracket. And then it's just a case of plugging in the expansion for S in the square brackets. Okay, so we've got T out the front. Now we put in the square bracket bits. So we're going to have a bunch of terms. So when we insert the identity operator, so the first term in my expansion, I get something that's simple. Okay, it just involves creation and annihilation operators. The next term is going to go like minus I lambda over 4 factorial. And also pull out the d4x outside of the vacuum expectation value with the zeros, and we will get AP1, AP2. Oops, there should be an A there. AP2, phi to the 4x, A and AKB between the 0 states. And, we can keep going if you want, until you run out of energy. So the next term, it's going to be minus I squared over 2 factorial lambda over 4 factorial. We would have a d4x, a d4y, 0, p1, ap2. We don't have x and y, so many more fields appearing between our vacuum states. And, as I said, you just keep going with this systematic approach. Okay. But what you see here is that we have, the way of running it here is we have terms that are ordered by this parameter lambda. So our coupling constant is acting as an expansion parameter. So if we are in a regime where lambda is a small number, this expansion that we have, which is ordered by this coupling constant, we're going to find that it will, should be a square there. We're going to find that when lambda is small, each term that we add is going to become less and less important. Okay, so at some point it's going to be a good approximation. Lambda is very, very small. It might be a good approximation to just keep the first term in our expansion. Lambda is sort of middling in size. We might have to keep a couple of terms, so maybe the first plus the second. Okay, but it's in principle under control. We know how to deal with this, right? It's a case of if we need more precision, or if we be careful, because this isn't a series that actually converges. It's not quite the case that you can in principle calculate an infinite number of terms and you get infinite accuracy. But it is the case that as you add in more terms up to some reasonably large number, some large power of lambda, that it does converge. So certainly up to something like lambda of 10, it'll get better and better and better. Okay. So we have this expansion. What we do next then is that we're going to have to deal with each term case by case. But at this stage, it's just enough to just plug in S. Oh, I didn't actually write it down. Let me clear. So step 3, plug our expansion for S to the amplitude into A. In this case, it was A 2 to 2. Okay, so that's what we've done in this step. Okay, so you can see that in general we have lots of expressions here with operators sandwiched between the vacuum state. And moreover, we have this time ordering that will come to the front of every expression. Okay, so in step 4, we want to simplify our expression, these time-ordered expressions between vacuum states. And we're going to do that by using a special theorem called Wix Theorem. So we're going to see that Wix Theorem is going to allow us, if we use it correctly, to simplify this expression above. Again, Wix Theorem is something that you can just systematically apply to the steps or to the calculation that we have. So I'd better tell you what Wix Theorem is, okay, or what it says, why it's so useful. So let me just state it. I'm not going to prove it or anything, but it'll be sufficient for us to just state it. Okay, so Wix Theorem says that if I consider the time-ordered product of n, in this case, n field operators, this is equal to the normal ordered product of my n field operators plus the normal ordered product of all possible what are called contractions of these fields, so phi1, phi2, phi(n). Okay, so let's just make sure that we understand the notation. So this T symbol is this time ordering symbol that we've met before, so it moves all of everything that happens later to the left-hand side, so it'll move all the late things to the left. It's normal ordering symbol it acts to move all of my annihilation operators to the right. I have an expression, all my annihilation operators will go off to the right. And I've introduced this term contraction. So to contract fields means join together two fields. So contractions always occur between pairs. Contract two pairs, and we replace them with a special object. Special object that we replace them with is something that we have met. It's the thing which is the Fineman propagator. Remember, we introduced this special propagator, df, which depends, so it tells us about propagating from one space-time point y to another space-time point x. So remember, the Feynman propagator was special because it also had this time ordering built into it. Okay, so that's tell you about the notation that people use for contractions. Okay, so contraction between a pair of fields, between two fields, written with a little connecting line above the two fields that you want to contract. And what we do is we say we replace these with this Feynman propagator. So let's do it x1 minus x2. So we use the labels on the fields here in the space-time points. Let's look at what Wix theorem says then for the simplest case, which would be a pair of fields. Let's do t, phi1, phi2. So it tells us take the normal ordering of all of the fields plus the normal ordering of all possible contractions. Okay, so what we end up with is n phi1, 2, and then here we've contracted these fields, so we should replace it with the Feynman propagator. And when we do this, we see this normal ordering operator is completely redundant because we no longer have fields. We've replaced them with a Feynman propagator. So this is redundant. We're just going to delete it. We could do a more complicated case. So above we had phi to the 4 interaction. So we had terms with at least 4 fields in them. About this case, so again, Wix theorem will tell us 1, 3, 4, so the normal ordering of all 4 fields, plus then the normal ordering of all contractions. So let me write down some of them. There's a lot of them, so I'm not going to go through all of them. But we can contract 1 with 2, and then we still need to apply the normal ordering to the remaining fields. We could do, what could we do? We could do 1 with 3. And we still have the normal ordering of the ones that are left, so it's 2 and 4. And we can keep going that way, so where you contract one pair and you leave one pair uncontracted. Many more terms. They're all in the dot, dot, dot. And then we also have the cases where we contract 2 pairs, because we have 4 fields, we can do that. So we'll have terms like this, where we contract 1 and 2, where we contract 3 and 4. You also imagine doing 1 with 3, doing 2 with 4, then there should be one that's left, which is 1 with 4 and 2 with 3. So as you can see, in principle, you get many, many terms here. It doesn't perhaps look like we've helped ourselves that much, because we're going to still have to deal with all of these terms in some way. However, we go back up to the expression for the amplitude, we see that we're not only interested in the time-ordered product of fields, but we're interested in the time-ordered product of fields when they're sandwiched between the vacuum states. So we see that because of that, it's going to simplify things considerably. So we we are interested in like this. So we have this time ordering, but then we sandwich it between the vacuum states. So this is going to be, very schematically, well, Wix theorem tells us we can write this in terms of a bunch of normal ordered fields, okay, plus dot, dot, dot. So we should think about what happens to these normal ordered fields between the vacuum states. So here's something important simplification that we have. So the normal ordered operation acting on any product of fields, what it will do is it will move all of my annihilation operators to the right. This is what n does. So as long as I have at least one annihilation operator in my expression, in my anything expression, I'm going to move it to the right where it's going to hit that vacuum over here, and it's going to return 0. Okay, so this is going to be 0. So anytime I have an n with any fields in these types of expressions, I simply get 0. So let's look at an example. So 0 with t, look at phi1, phi2. We saw above what that is. So it's n phi1, phi2 plus the Feynman propagator. Going to be 0, 0, n, phi1, phi2, 0, x, 1 minus 2. And then, as we said, n, anything, this does contain annihilation operators, acts on the vacuum and simply returns 0. So just left with the Feynman propagator piece. So this is good because you should recognize this is our definition of the Feynman propagator. You remember back a few lectures ago, we defined the Feynman propagator to be the time-ordered, well, exactly this time-ordered product of fields. Okay, so we've just, Wix theorem certainly works for the case of 2 fields. Okay, and if we applied it to the case with 4 fields, we said with 4 fields, we get all of these terms with n's in them somewhere. There's going to be a lot of them. And we end up with only 3 terms that don't have n's in them. So when we sandwich it between the vacuum states, we're only going to be left with these 3 terms at the bottom, which we can express in terms of Feynman propagators. So what we'll end up with is the following. So we do the contraction of 1 with 2 and 3 with 4. Plus the contraction of 1 with 3, 2 with 4, and the contraction of 1 with 4 and 2 with 3. Okay. So we have, with Wix theorem, we see that we are able to simplify these expressions down into objects that we know about, namely these Feynman propagators. Okay. So that is step 4. Okay, so we want to use this Wix theorem to simplify our expressions in general. Okay, so we have reached time where I should pause because we reached the end of the lecture. So let me summarize what's happened so far in this lecture, and then we'll finish the discussion obviously in the next lecture. So far in this lecture, what we've done is I've tried to argue using scattering theory why the S matrix is simply this time evolution operator evaluated at plus and minus infinity. Okay, so that's nice because it gives us a concrete expression for what S is. So it's the time-ordered product of this exponential. And we said there were 2 ways you could write this. There is an integral over dt, or if we use the Hamiltonian density, over the full d4x expression. Okay. That's what we want to calculate. We said it's tricky, or in fact impossible in most theories, to actually calculate this. So we need to, the approach we use is Dyson's expansion, where we simply expand out this exponential as a series. Okay, and you order it term by term, do this calculation term by term by term. So we started to go through these this 5-step process that you can work through, that should work for any theory, in order to calculate a scattering amplitude. Okay, so we've discussed the first 4 steps. So first one was deciding on the process. Well, that's easy. The example we're looking at is this 2-to-2 scattering process. We then said we had to write it in terms of vacuum states. Again, reasonably straightforward. We know how to do that. The expansion of S, that was straightforward. And then plugging our expansion for S into the amplitude, that was also reasonably straightforward. We started, or well, I stated that we should use Wix theorem then to help simplify this expression that we have. We've substituted the expansion in for S. So we've started to see how that can happen, because Wix theorem allows us to convert time-ordered products of operators into Feynman propagators for things that we know how to deal with. Okay, so in the next lecture, I'll finish the discussion, obviously, of step 4, and we'll reveal precisely what step 5 is, so how to complete the process of calculating the scattering amplitude.